Okay, hey everybody. We're going to take notes today. There is a document in Classroom called Review Notes 1, Foldable 1. I actually have 5 of these coming your way in the next couple of days so that we can move really quickly through all the material we covered this year. And while we do that, while we go over things, we're also giving you a foldable so that you can use it like a whole deck of flashcards so that you can do your own studying. So I'll be trying to hit all the high points and I'll be using the document camera. And hopefully those of you at home are following along and making notes. If you're using notebook paper, just take a blank piece of notebook paper and give it a hot dog fold like I'm doing right now. So I'm going to write only on the right-hand side of the fold today. And then later on, when you have more time, if you're on notebook paper, there'll be video of this. You can take a look at it and you can go back and write down these prompts. So these are like one side of the flashcard. These will be like the answers side of the flashcard. You ready? Looks like we have a few people racing back from their printers. That's okay, I'll pause in one moment. We're going to start with average velocity versus average speed. Do you remember what that difference is? The difference is based on displacement because average velocity is based on displacement. So that's where I'm going to start. Just watching for Austin and Jason and Rodrigo and, oh, you know what? This would be a perfect time for me to take roll. I can look at your high chats. But I can also look at your faces right now, which is kind of nice. By the way, yesterday's STAR testing went really well. I saw in the news that it was, the news reported it was terrible because the state had a big problem. They did have a problem for students who had accommodations to have the test read to them, I guess electronically or to be able to answer digitally, but that was not most of the students in the school. So most of the students in the school did just fine. All right, I see Austin's back, Jason's back, Rodrigo's back. I think we're ready to go. Screen share working okay for you? My fingers wiggling? No? Oh, I'm so glad you told me. Yesterday I made a video. It was 32 minutes long using the document camera, and I finished. The screen share was frozen the whole time. And it looked normal to me. That was the worst part. But I was like, oh, this is what my students are telling me sometimes when they say no. You know, that's why I've started wiggling my fingers, or did start wiggling my fingers a while ago. How about now? Wait a second, I lost you. Okay, good, thank you. I don't know why. The Windows whiteboard icon has replaced my cursor. Go away, Windows. Whiteboard, don't go away, Windows. Okay, ready? All right, so the first prompt is about average velocity versus average speed. The differences between them are based on displacement because velocity is based on displacement, speed is based on distance. So let's use this whole margin because as you see, we're really going to crowd this. So remember, we're trying to keep this lane where my pen is free so that you can put a fold there so that when you're looking on one side, you don't see the prompts on the other. So speed is distance divided by time. So I'm going to draw a track here. So this is either a racetrack for a racehorse or it's a school track around a field, you know, for track and field. So if that's you and you run all the way around the 400-meter track, your distance is 400 meters, right? So your speed would be based on that. If it's a horse, it's probably a 1-mile track. So it goes all the way around, right? So we'd have 400 meters divided by time. But, hold on, somebody's reconnecting. But if you look at velocity, which is based on displacement, so velocity is delta D over T. If that person starts here and goes all the way around and comes back and stops here so that their change in position is 0, delta D is 0 and velocity is also 0 because velocity is based on displacement. So I know that looks kind of small and funny, but you know what? We're just taking shorthand notes of concepts that we studied in more detail to try to sort of remind us about these ideas. So here your velocity is based on, your speed is based on 400 meters of distance divided by time. And here you've got 0 velocity, okay? So when we get velocity like this, change in position over time, that's an average velocity. So that's V average. And it's probably going to be delta X a lot of the time, right? Horizontal and on the ground. But remember that there's another way to get an average velocity. If you take 2 velocities and you add them together and then you divide by 2, That is also an average velocity, and you'd be surprised how often that simple idea is really crucial in the AP exam, okay? So hang on to that thought also. Now we have question, what is the slope of a position time graph? If I zoom back out, I can see that a little bit better. Slope of a position time graph is velocity. What is the slope of a velocity time graph? Well, you know what, let's draw some. So I'm gonna make some little tiny graphs about the size of maybe 2 thumbnails. So this one's gonna be position, I'll put X versus T. And in a vertical stack, this one's gonna be velocity, put V versus T. And I'm making these really small, and I just realized I only have first quadrants, so here's a little one with the first and a fourth quadrant, just to remind us that that's also possible. So when you look at this thing, what's the slope mean? Well, the slope right here is change in X over time, right? There it is. So that's why the slope of a position time graph is the velocity. So you look at the position time graph and you get the numbers off it. You can go down using the slope, you can go down our stack and actually plot the velocity graph. There's a single slope there, right? There's only one slope. That means the velocity value is the same everywhere. That means we have constant velocity. If you look at the slope of that thing, you can go down because that slope is change in velocity over time. That's acceleration, right? The slope of a velocity time graph is acceleration. Acceleration is equal to change in velocity over time. So the slope is how we use this stack as kind of a graphic organizer for our brains. Go down the stack with slopes. Now, what happens if you go up the stack? Well, if you look at an area right here, let's suppose we had some. I don't know what it is, but suppose we have some area right there. It's like a little box, isn't it? It'd be A times T. Rearrange this, A times T, right? So if I get the area under the curve on an acceleration time graph, that's going to be change in velocity. So this is going to be area gets me delta V. How about the area underneath a velocity time graph? That area would be V times T. Okay, if you look right here, average velocity times time, that's going to equal your change in position. So that's going to be delta X, and it's area that lets us work our way up the graph stack. So the area under a velocity time graph is equal to displacement. In other words, not the actual position, the change in position. Remember, displacement can be delta X, like I've drawn, or delta D, or delta Y. Any of those terms are good terms for displacement. Good abbreviations or symbols. Average acceleration is right here. If you've got an overall change in velocity divided by time, you don't know what your acceleration was necessarily every instant of that time. So if you just have like a final one and an original one, and you divide by time, that's an average. Any questions so far? Please remember, you can slow me down anytime. Just say, wait. You can stop me anytime, make me go back to something, clarify, repeat. No worries. I want this to be useful. I want to make sense. Okay, 3 main motion equations. Well, that one right there is actually the same as this one right here. Instantaneous velocity equals original velocity plus acceleration through time. So at the beginning of the year, I was careful to put an F there all the time because it really helps students sometimes to recognize that there are 2 velocities, so final and original. And I want you to recognize that that is a function of time. So when you put in a specific time right there, you get a specific velocity. Please recognize and use your math skills. So that is also y is equal to mx plus b, right? So that is the instantaneous velocity would be b plus mx in this case. So the slope right there, that acceleration is that slope right there. Okay? Second one is not linear. The second one says change in position, maybe delta x, is equal to original velocity times time. So it looks like it's just this velocity equation for average velocity, but it's not the whole story. That's just the first part of it. So original velocity times time plus 1/2 at squared. That one is not linear, is it? That one's going to be quadratic. So maybe something going up in the air and falling back down. That would give you its position as a function of time. And then we have the VF squared equation, which a friend of mine calls the 222 equation. Okay, because there's the first two. There's the second 2. And there's the third 2. 222, I don't know what he says. Looks like 222, okay, I got it. Okay, so those are on the AP equation sheet. Why do they look different here? Because I calculated displacement. On the AP equation sheet, they say x minus x original, okay? But that's where they are. This one's convenient when you don't know time. Acceleration due to gravity, negative 9.8 meters per second squared. But you guys know that, right? I'm supposed to be teaching you new things every day. So here's another one. Negative 32. Did you know it's negative 32? They could throw that at you, okay? That is the magnitude if you're using feet per second. Strange English units, okay? Used to a long period of human history. All right, now, vertical launch, velocity at the maximum height. That is 0. 0. Vertical launch, acceleration at the maximum height. That is not 0. A equals negative 9.8 meters per second squared. 0 is the velocity at the top. You can have a velocity of 0 and still have that acceleration. Really an important concept, very frequently missed by students. So likely to appear on the AP exam, okay? Remember, there are 2 ways to accelerate. You change your speed or you change your velocity. So if you're up there at the top, ooh, sorry, Shelby's trying again. If you're up there at the top, right, and you are, you're looking at a projectile that's going up, it's got a whole lot of speed change happening right up at the top, as well as direction change. Because it's got to go slower and slower and slow to a stop. And then it has to stop for an instant. It's got to stop going up. And then it's got to change direction and come back down. So the acceleration does not go to 0 just because the velocity does. Hey, Shelby, have you got sound? Yes? That's awesome.
I do now.
Yeah. Yay. All right, rebooting fixes everything. So strange. Just like it did in the 80s and 90s. It's crazy. Can you imagine every time, I don't know. It used to be you'd have to reboot like 3 times a day. It was a funny story about somebody just wrote a comparison between what if your car acted like your computer? You'd have to just stop and restart your car repeatedly through the day. It's crazy. But anyway, sorry to keep you waiting, Shelby. We're about halfway down this page, but I will post a video later and I'll try to remember to post it for you too, not as an assignment, but as something you can use as a resource. Okay, so you can catch up on those. Okay, so those are vertical launches. So what we mean by a vertical launch, I'm drawing over here on this side, is straight up and straight back down. When that's true, the acceleration is negative 9.8 at the top and the velocity is 0 at the top. But it's also possible to have angled launches. So let's feel free to write on the left-hand side, because remember this left-hand side is supposed to be for you to ask yourself questions later. Is the velocity at the top 0? No, it's not when it's launched at an angle. When it's launched like this, something at the top is 0. That is, the y velocity at the top in the y direction is 0. But the x velocity is not. That is, it doesn't stop. Even though we use that often as a problem-solving technique, we can use it because it stops going up, but it doesn't stop. Keeps traveling sideways the whole time. Okay, the x component of a velocity vector. Well, this is the idea now of something launched up at an angle. So if I have something launched up at an angle like that, what is that x component like and what's the y component like? If you have the foldable there, I think it might make sense to reverse these. I'm gonna go change my original after this year. I'm gonna put y there and x there, just because of how we draw the triangles. So if you can change that, feel free. If not, don't worry about it. I'm not sure what you're working with there, but I'm gonna draw something at an angle right here. So there is an original velocity launched up at an angle. Now, when it's launched up at an angle like that, it's going up and sideways. Therefore, its 2 components need to be up and sideways. Do you see how it's up and right? So one of your components is going to be called up, right there. And we call that VOY, okay? And one of your components is going to be called sideways, right there. And we call that VX. It doesn't have to be VOX because the velocity in the X direction will not change. This is the launch angle. Notice that Vx is adjacent to it, so that's going to be the original velocity times the cosine of the angle. Notice that the y component of original velocity is opposite the launch angle. So that means it's going to be calculated with original velocity times the sine of the launch angle. That's why I was thinking it'd make more sense to put y up there and x down there. That's how we always draw them. Okay? So AY is equal to negative 9.8, right? Meters per second squared. I'm off camera, sorry. Get over there. AX equals 0. It's all vertical. Okay, we have a prompt here for velocity, magnitude, and direction. And this could go for displacement also. I mean, these might be two distance. If I get rid of the V's and I just say somebody walked that path to the right, and then they did a 90-degree turn and walked that path up the page. If I were asked to find their displacement, I'd have to go from the original position to the final position. Or in this case, as drawn, if I'm asked to find the resultant velocity, maybe I'm just given the components, I need to use the Pythagorean theorem. So velocity, magnitude, and direction, use the Pythagorean theorem. Is that okay if I just write that as your reminder? So in other words, that original velocity is Vx squared, the square root of Vx squared plus Vo squared. Now, what if I need to know the angle? If I was not given that angle, but I was given the two components, or somehow I'm able to calculate the two components, I can see what the tangent is. Tangent is opposite over adjacent. So it's VOY over VX. So that means if I need to find theta, that's the inverse tangent, so I'm writing tan to the -1. Hit the second button on your calculators, right? Of VOY divided by VX. And again, same thing if it's a displacement problem. That would be the portion of the displacement in the north or y direction. This would be the portion of the displacement in the x or east direction. All right, now, what is the only formula it says for horizontal direction? That is all based on this idea that acceleration in the x direction is 0. So if I go back and I look at my motion equations, right? Look at this middle one. Put a box around this right here. If we're looking in the y direction, acceleration is 0, you only have that, okay? So when something is happening in the x direction, I'm sorry, I should have said, when you're looking in the x direction, acceleration is 0, right? So you only have that portion of the equation. So when they say down here, horizontal direction, what is the only formula? Delta x displacement, right, change in x position, is equal to the velocity times the time. And that's assuming, of course, the velocity is in the x direction also, okay? And this is a pitfall. This is what a whole lot of students fall right into. This is a tiger trap. This comes from this idea up here, right? Our definition of velocity is change in position over time. And so people will use this when they shouldn't. This is not valid when acceleration is present, okay? So when you look at this equation, you can see the whole story. So if you use just this first part when acceleration is present, you're going to be all wrong about how much displacement actually occurred. Okay, so we're going to write that down, and we're also going to write never use, and I'll put the other version of it also. This would be V equals delta x over t, right? When acceleration is present. If you want to be shorter about that, you can say with acceleration. But if you have acceleration, you're going to get that wrong. Okay, so watch out for those. Okay, the horizontal shot here is the idea that something is launched off a cliff like that with a perfectly horizontal original velocity. So what's 0? Tell me something that's 0, Bursum.
Well, if it's the horizontal acceleration would be 0.
Awesome. AX is equal to 0. Now, important problem solving trick. Something else is 0 also. What is it? Elliot, do you know, and are you there? Can you come on screen if you're there?
Sorry, what was the question? I was writing something down.
Okay, what else is 0? So I'm pointing at this right now. Bursum gave us this one. What else is 0 for a horizontally launched projectile? It's hard to remember. This is from a long time ago.
Would it be the velocity in the y direction?
Ah, beautiful. Way to go. velocity in the y direction is also 0 originally, right? The original y is 0. And so that's super useful in problem solving. So if I go back to this equation up here, again, see that one? And I'm looking in the y direction now, it's the original velocity that's 0. And so I have the second half of the equation in use, which gives us a really useful formula. So I'm going to try to squeeze this in over here. Time to fall. Do y'all remember that one? So if it's horizontally launched, it acts as if it's dropped from rest in the y direction. The square root of 2h over g is how I'm going to write it. 2 times the height of the cliff divided by the absolute value of negative 9.8. Does that make sense? In other words, 2 delta y divided by a, if you do the full equation. But that's a way to write it with just absolute values. 2 times the height divided by g. So this thing right here is h for the height. Okay, time to fall equation, super helpful. Okay, now that works also, by the way, right? If you're using components, because you can work with original velocity times the sine of theta also to make that happen. Okay, Newton's laws of motion. So take a look at what we just did. We just went through all of kinematics. That is all of our mathematical descriptions of motion. So that was, I don't know, August and half of September. And now we're moving on to dynamics, which is force, or the study of why things change their motion. So remember, we put a few prompts over here. You can add things to the left-hand side to use this more like a flashcard, right? Where there's something over here. So you and your friend could ask yourself a question. Okay, talk to me about a vertical launch. Sorry, the document camera is adjusting slowly. Get white paper behind it. Okay, so you're looking at this and you're saying, okay, tell me what you know about a vertical launch. And you go, well, let's see. Acceleration at the top is not 0. Velocity at the top is 0. And then you can open your foldable, flip back and forth and see those ideas. Okay, next, Newton's laws of motion. You're all ready? The TEKs say you need to know which one is which. And I think that's wise also on the AP exam. So we're going to start with the first law. So the first law is the one that says an object at rest remains at rest. So I'll go dot, 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 at rest. And an object in motion remains in motion, unless or until acted upon by, okay, dot, dot, dot. That's the first law. So what's it really telling us? Unbalanced forces cause accelerations. Unbalanced force causes acceleration. That's huge. If you want to know about force, watch for acceleration. Corollary. If you want to know about force, watch for constant velocity, right? If you see constant velocity, you know that the forces sum to 0. There is no unbalanced force. It is also about inertia. That is the tendency of an object to resist change in motion. So if it's already moving, it's going to tend to just keep moving. If it's at rest, it's going to just tend to remain at rest. And the more mass it has, the stronger that tendency is going to be. Inertia is measured in kilograms. You do not have to be moving to have inertia. Every object has inertia. Okay? Second law. That's the one where people say F is equal to ma. Isaac Newton, though, wrote it like this. Acceleration is directly proportional to net force and inversely proportional to mass. Okay, that's second law. Third law. Instead of writing all this out, let's just write hand clap. Hand clap. I think that might be enough of a reminder. When I clap my hands together, you clap your hands together. First of all, you have to have 2 objects. You cannot clap with just one. So when object 1 exerts a force on object 2 exerts a force on object 1 at the same instant that is equal in magnitude and opposite in direction. Okay? That's third law. Now, you can never see the third law in a free body diagram. Never in FBD. Because remember, a free body diagram is supposed to show only one object. So there's a trap for you. They will sometimes create a situation where they try to get you to say that the normal force is equal and opposite to gravity. That's like an action-reaction pair. They're not action-reaction pairs. Because if the Earth pulls on the object, the reaction pair to that is the object pulls on Earth. So remember how we do those 3-word sentences? Blank pulls or pushes on blank. That's what you want to use for third law if you're looking for an action-reaction pair. So forces come in pairs. I'll just write forces in pairs. That's third law. Questions? Now, weight right there. Weight is an example of the second law. It's just, I should say, a specific variation of the second law. So if force is equal to mass times acceleration, a particular force called weight is equal to the mass times the acceleration caused by a planet pulling on that mass. So there is F is equal to ma, right? So weight, the pull of a planet acting on a mass. Okay, in the little bit of space we have left, we are going to cram in elevator problems and Atwood machines. Now, when I draw this elevator problem, I'm going to draw a very short pair of arrows, one up and one down. So I want you to realize that everything we're saying right now about an elevator problem applies to anything else with forces like that, such as a helicopter, right, with the force of the air under the rotors lifting up and weight pulling down. A rocket trying to go up or actually accelerating. A bucket being lowered into a well by tension on a rope, okay? All of those things apply. But when it's an elevator problem, I'm going to call this up FS, the force of the scale, because that's the type of problem they like to ask. Now, if you're standing on a bathroom scale, that would look like N for the normal force. Call it the force of the scale anyway. If you're hanging from the elevator by a spring scale, you know, you got like a produce scale hanging from the ceiling and you're on it, you might want to call that a tension force. Don't call it the force of the scale anyway. Doesn't matter what kind of scale it is, okay? If it's an elevator cable, you're hanging onto a cable, you could call it T for tension, but I'm going to put it as the force of the scale. Remember that a scale does not measure your weight. Scales don't measure your weight, remember that? They measure their own lifting force. We know that because when we put them on elevators or we put them in any situation where there's acceleration, they get screwed up and they don't read your weight. They read their own lifting force. So here I would take the sum of all forces equals the force of the scale up and the weight force down, right? So actually maybe I'll put a W in there, okay? So we can talk about accelerations. This one right here is MA, okay? This one right here is MG. Remember that G is for the weight. That's gravity's acceleration. It's not gravity. That's not force. Gravity is force. That's acceleration. This A is the actual acceleration, okay? So when you rearrange all that, substitute in and rearrange all that, this is what you get. The force of the scale, the force reading on the scale, is equal to mg plus ma. Let's pull out the m's. So look at this. This is going to tell you about weight and the reading on the scale. When the acceleration is positive, the reading on the scale is going to be bigger than mg, isn't it? Something's been added to it. It's going to be bigger than the person's weight. When the acceleration is negative, this is going to be smaller than mg. It's going to make it look like the person lost weight. In other words, the scale doesn't have to lift with a force equal and opposite to the weight. Okay? So this drives me to the other side of the page. So I'm going to write here 2 ways for negative acceleration, question mark, and 2 ways to have positive acceleration, question mark, because that's really important to remember. So remember, you can put other prompts over here. Okay, so what's negative acceleration? What's positive acceleration? Well, in this situation, it really matters. It really affects your calculation. So if the elevator is moving in the positive direction and slowing down, that's negative acceleration. But if the elevator is moving down and going faster and faster, that's negative acceleration also. Okay, so faster in the negative direction or slower in the positive direction. Those are both negative acceleration. If you have negative acceleration, in other words, you don't know if you're going up or down. You don't know if the thing is going forward or back if all they do is tell you that the acceleration is negative. Because it's possible to have negative acceleration going forward, and it's possible to have negative acceleration going backwards. It's possible to have negative acceleration speeding up. It's possible to have negative acceleration slowing down. So you got to watch that. What are the two ways to have positive acceleration? Faster and faster in the positive direction, or slower and slower in the negative direction? If you're coming to a stop in the negative direction, that's kind of the first step in becoming positive again, right? All right, good quizzy stuff there. Okay, an Atwood machine. An Atwood machine is two masses connected over a pulley. So there's my pulley symbol. And typically we have a big mass hauled up in the air, rope over the pulley. And then there's a little mass down there. And so when you let it go, it's going to accelerate really rapidly, maybe, because the big mass anyway is going to come down and the small mass is going to go up. So please sketch that. It's a great question for a test for them to ask you about, because it puts you through your paces. For one thing, you can demonstrate that you know you need two free body diagrams. You cannot have a free body diagram if your body is attached to another body. So you go separately and you draw separate force diagrams for this mass and that mass. That also means you need two net force equations. The whole reason you draw a free body diagram is so you can look at it and it shows you what the forces are to list as you write that net force equation. The other thing you want to know is that you should be following the Atwood convention such that your direction of motion is positive. You can't say up is positive and down is negative in this situation. Gravity pulls the big thing down, which means gravity is also pulling the little thing up. So you need a system of signs so that that's one direction. Down for the big one is the same direction as up for the small one. So you would be able to drive and justify everything if you could, sort of do that problem from scratch. If you're in a hurry and you want to take a shortcut that's valid, use Newton's second law. A is equal to net force. So I'm going to write that as A is equal to Y, question mark. Why is it moving? Because there's a difference in the weights, right? The two different masses are being pulled down by planet Earth. That's two different forces. The difference in the weights that causes it, that's the driving force. A is equal to F over M. Why would it not want to move? Because total amount of mass equals total sluggishness. So the way that would look is, this would be, I'll just say big M is the big mass. So it'd be big mg minus little mg, right? There they are, the difference in the masses times g, divided by the sum of the masses. The total mass is the total sluggishness. This is Newton's second law. There's net force. There's total mass. Now, it is possible, we've never seen this on an AP test, AP1 test, but remember they've only had AP1 tests for what, 5 years, okay? So it's possible you could have a situation where there's what I call a half Atwood machine. That is, there's an object sliding on a table and the pulley's on the end of the table and the dangling mass is over here. And there's friction on the table. There could be, right? Friction would go that way. If you get something like that, you'd have to remember to include friction in your forces, because friction would be battling the tension that's pulling it forward. So we have not seen one of those on an AP1 test, but the same technique would apply. You need two free body diagrams, two net force statements. The direction of motion is positive. You could handle it because you know how to do this. Wow, we did a whole page. Okay. I think you need a break. Excuse me, I think my voice does too. Need a break? You can take a break, but don't go yet. Do not take a break until the end of the period, all right? But I'm going to give you an assignment to do now, and you may leave Zoom if you wish while you do this, because it's a video assignment. I know that helps with bandwidth. So let me stop share for a minute. Do you have any questions about that? Do you see how you could use that foldable to quiz yourself? Maybe, hopefully. Okay. Zooming in on another screen to show you. All right, then, here's what we're gonna do. Don't anybody go anywhere for at least 1 minute because I need to take roll. So just take a break for a second while I finish taking roll. How about that? Because I got part way through before. But while I'm doing that, you might be able to read that share. I don't know how small that is. Or you can just let your brain rest after all that work. You know, when I was talking earlier about if you come to school, stay home tomorrow. I know obviously you're not coming to school if you're home, but I was wondering if there are people who like come on Tuesdays and Thursdays only because of the classes or practices that they have, and they stay home Monday, Wednesday, Friday. Is there anybody like that? Do people do that? Yeah. Cammie Jordan, are you here today? Okay, so just Cammie and Anna, it looks like. Okay, cool. Now, all right. Is my screen share showing you Google Classroom? Thanks, Kyan, and others who are nodding. I appreciate that. Thanks, Jason. Okay, so you have 2 to-do cards in the AP College Board. You should be able to finish this before the period ends. I will double check, but I don't think we have anything for advisory today. We did not have anything for advisory as of Monday. I'm sure. When you think of it, we don't have anything for advisory. So these to-do cards are part of your attendance today, okay? So I want you to work on these videos. There is a worksheet, okay? And you're supposed to submit the worksheet. It's a Google document, so you can type on it, highlight it, or, you know, do it on paper and hand it in. Either one of those things is fine. So you're going to be learning something here that's really important because this is something that has occurred multiple times on the AP exam for AP Physics 1. So let me get back to document camera again. Okay, is it live? Can you see my fingers? Yes. Okay. So the deal is, if you have something like, trying to find a scrap of piece of paper here. If you have something like this, or a denominator, like, you know, A is equal to F over M, it's really, really nice if somehow or other you could turn that thing into a line. Because if you can turn your relationships into a line, you can use like Y is equal to MX plus B. And that, if you're clever about arranging things, the slope of that line can give you a quantity that you're looking for in lab, okay? So that's what you're gonna see. You're gonna see linearizing data in the second of the 2 videos, so video 3. So video 2 shows the data being collected and how it's done using a piece of equipment that you have not gotten to work with. I don't have one in the room, but they are common. And they could easily ask you an experimental design question where you want to suggest using that piece of equipment. Or they could give you an experiment where they're telling you that a student did use this equipment and these are the results. So I want you to know how a fan cart works, and you need to know how to linearize data. So that's the topic for these 2 videos, okay? So at this point, I'm gonna say goodbye to you on screen if you want to. You're welcome to get off. I will be here though, pop out if you have questions. Go do that assignment this period before this period ends. Thanks, bye. Or stay.